So if you do miss a class, what I'm doing is well, it's already been there, but on the bulletin board page, you should see the link to Zoom, so you can join that way if you need to. And then there's also a place that links to a YouTube channel, just says Mr. Webb's YouTube channel. And I'm gonna be posting the videos from the classes that we have just on that. So if you ever miss and you wanna see what we did, I will sometimes record the whole lesson, sometimes record part of it. If there's part of it like today where you're just working on a worksheet and answering questions and practicing, I probably won't record that part, but I'll record anything that's instructional and then post that. And so if you just go to bulletin board page of Access, look under the links and click on Mr. Webb's YouTube channel, then you'll see a playlist for AP Physics 2, AP Physics 1, and CP. And so just go to CP Physics, College Prep Physics, and then click on the day. I'll just title them with the day. So you'll know, oh, I missed that day, that's the one I should watch. Okay? So that way, if you ever need to attend by Zoom, you'll be able to. If you ever need to watch the video, you'll be able to. And then in the announcements on that bulletin board page, that's where I'm gonna put like a quick synopsis of what we did each day. So if you miss it, you can just look on the announcement and say, oh, on Wednesday, January 5th, they did this. So you'll be able to check on the announcements, watch the video on the YouTube channel, and join by Zoom if that fits your needs. So I think probably for the next few weeks with both COVID and flu and all kinds of cold illnesses and stuff, there's going to be people in and out quite a lot over the next probably month. So I expect for the next few weeks to be using that as needed. Any questions about that? Just where to find what you need to join or to catch up if you ever do miss? All right, a couple quick comments on the exam, and then we'll jump into the lesson for today. So let me unblack this so you can see the agenda here. For the exam, the grades were pretty good overall. I mean, obviously, some people are more naturally gifted at taking tests and others struggle a little bit more with it. That's just, and sometimes you're typically good at taking tests and just have a bad day. So, there's no perfect answer for any of that. But the highest score was around 97, I think, percent. And so I did end up giving just a little bit of a curve. I think I curved it to like 96 or something, or 95, somewhere in that realm. Just dropped it a little bit to give it a tad bit of a curve to it. So the grade that's in Access is giving that curve. So I think it was maybe like 110 points possible, and I curved it down to made it 106 or something just to reduce how many points possible. So it wasn't a huge curve, but just a little bit of benefit there to add a percent or so onto the grades. If you would like to see your exam, I did keep them here in the room. After a couple weeks, I'll probably put them down in the locking storage cabinet, the file cabinet and stuff. But for now, I'm just keeping them up here in the class so that if during a lunch or after school, if you want to come by, if you want to look it over and see what you missed and just discuss it with me, you're more than welcome to do that. I will be, I think, much more available this semester after school. I know many of you knew about my daughter having some health issues, and the pregnancy was pretty rough for her. But right during exam week, she and her family were able to move to Texas and reunite with her husband, who's in the Army there. And so they were all together over the holidays, and they're settling into their new home. And she had her baby yesterday, so the baby's healthy, she's healthy. So we're kind of past all those days of emergency runs for me having to go take care of the grandkids and all that stuff. So I think I should be able to be here after school if you need to meet at those times. And as normal, I'm generally here just during lunch working. So you're always welcome to come by either time, whether you need help on things we're doing now or if you want to look over your exam. So, but I appreciate those of you that said you were praying for my daughter and her family, because it was a tough time. That month of November into December was pretty rough for them. So I'm glad they're settling in and doing well now. In terms of what we're going to be doing this semester, we're going to continue kind of where we left off. We had been talking about momentum and forces and kinematics and motion. We're going to continue with things related to that, but switching gears just a little bit. And then after a couple of units, we're going to switch gears more dramatically to things like electricity and magnetism and optics and things like that. But initially, our material that we cover is going to be very much related to what we did first semester. So some of the things you learned first semester, you're still going to need to be able to apply, like Newton's laws and the kinematics equations and things like that. You'll still need to be able to use for some of the things we do. The topics in this first unit, as we begin this semester, are work, energy, and power. And this will be a pretty short unit. We'll probably just have a quiz over this unit because we won't cover that much material. There's only one equation for work, there's only one equation for power, and there's only 3 equations for energy. So it'll probably take a couple of weeks. We'll see. It might be like a quest sort of thing where it's a little bit longer than a traditional quiz, but not quite a full 100-point test or something. So it'll be a little bit briefer, and then we're going to move into talking about things that move in a circle. So still how they move and what forces cause circular motion, and things like torque and things like that. And then we'll then start switching gears, like I said, into electricity and waves and other branches of physics. Today's goal is to have you start some notes on focusing on the first key concept there, work. We're going to define all 3, and then we're going to focus on the concept of work, and then we're going to solve some work problems. So we're going to do some work with work. And there's just a single equation that you have to learn. It's pretty easy. It looks a lot like Newton's second law, F equals ma. It's similar to that. And so it'll be pretty easy to use, I think. So any questions about any of that we've covered with just kind of updates or schedule? Yeah.
I have kind of a off-topic question. Do we still need all of our notes from last semester?
They wouldn't be bad to keep because, like I said, for at least for this first part of this semester, knowing the kinematics equations, knowing Newton's laws. I mean, I'm never going to collect your notes, so in that regard, it's up to you. But having them available to review might not be a bad idea, at least for the first half of this semester.
Okay.
Which I guess technically means that material will also be on the exam.
Yeah.
Because there's just so much that builds off of what we did first semester. Okay. Yeah. So you can make that decision on your own. I would recommend it if you're able to keep them, just because you may want to refer back to them. But there's nothing from first semester that I'll be testing you over that we won't be reviewing in class and using in class.
Okay.
So it's not like I'm just going to spring something from first semester on a test that we haven't been doing. But some of the things that we did first semester we'll still be using. So it'll only be the things we continue to use and you see in our lessons that would show up on a test. So they'll probably end up kind of being in your new notes and in your new assignments and things too. So not critical to keep necessarily, but just depends on how you use your notes. If you like to go back and look at them frequently to review, might not be a bad idea. Anything else? All right, so we're going to start with some key terms here, work, energy, and power, and we're going to define each one. I would recommend that you put these definitions into your notes because these are completely new, and you will be tested over them, probably multiple choice, matching, or fill in the blank kind of things to make sure you understand the definitions.
Is this like unit 5?
Let me check. The numbers are all different in all my classes, so I forget exactly what the unit number is for this class. I think it's unit 4 in this class, but. Oh, no, it is unit 5, you're correct.
Okay.
All right, so work is in some ways the most confusing of the 3 terms because we use that word in our common language all the time. I'm going to work, I have homework, I'm gonna go do a workout. Like, we use that term casually in common language all the time, but it means something really specific in physics. And so what you might consider to be work, as in doing a workout of some sort, may or may not be work in physics. So for instance, if I said, hey, can you get into a plank and hold it for a minute? You would feel like you're doing some pretty good work. I mean, your muscles would be working and the way we use that word, but in physics sense, you're not doing any work because you're not moving through a distance. And so This one sometimes is the most confusing just because we use the word so frequently to mean other things. And in physics, it's very specific. So here is the briefest definition that I could come up with, and it is when we apply a force to an object and that object moves through some distance. So the two key components there is we have to apply a force, and the object that we're applying it to has to cover some distance. So holding your body in a plank position, or doing like the, where you have to do like the hang on a chin-up bar and you just have to hang there for a certain amount, you're not moving your body through any distance, you're just holding it stationary. So those kind of exercises, your muscles are getting a workout, you're burning energy, but it's a chemical energy, it's not the sense of work being done in this regard. So something has to move for work to be done in the physics definition of things. Okay. If there's no movement, then no physics work was being done, even though it might have been a good workout for you physically. It has a little bit different meaning in this course.
What does application mean?
Just in some way you use a force, you apply a force, or you use a force to make the object move.
Okay.
So if I pick up this pin, I had to apply a force on this pin to make it move. All right, now here is another way to define it based on the second word we're going to talk about, which is energy. And so another way to define work is that it is the transfer of energy from one kind of storage mode to another. And I'll let you write that down, then we'll clarify what we mean by storage mode. And Lauren, you're seeing the notes okay on your side? All right, good. So you've probably heard the words kinetic energy, potential energy. I mean, I imagine those words make sense to you. You've heard those terms before. There's also spring energy, there's electrical energy, electrical potential energy. So there's a lot of different kinds of ways we see energy in objects, stored in objects. So if I stretch a rubber band, I'm storing elastic potential energy in that rubber band. If I lift something up on the top shelf, I'm storing gravitational potential energy into that object by giving it a greater height. And we're going to define all these kinds of energies as well, but just trying to give you some examples. If I throw a ball, I'm storing energy in the motion of that ball. We call that kinetic energy. Okay, so there's just different ways we might see energy kind of wrapped up in the objects that we're moving or adjusting their positions. And so we do work when we change the way the energy was stored. So if I have a box on the ground, it has very little gravitational potential energy because it's on the ground. But if I do work, I can lift it up and put it on the top shelf. By doing work on the box, I've applied a force and I've made it move through a distance. Now it's on the top shelf and I've stored more gravitational potential energy because it's higher. The higher something is, the more gravitational potential energy it has. Because if it falls off the top shelf, it could break something as it hits the ground. If it's already on the ground, it doesn't have any potential to do anything. Okay, so transferring energy from one kind or one sort of storage to another is another way we could define work. Now, energy is something, again, that when we talk about energy in common language, like energy drinks or have a lot of energy or I'm burning energy, most of the time it actually is something that we also would define in physics, but energy isn't really a physical thing, it's a transfer in a way. And so when we define energy, we usually define it as some sort of an ability. So we might say, and you probably have heard this before, it's the ability to do work. And again, here we're using the word work in the physics definition. Okay, not just generally work, but the ability to do work according to the physics definition. So we just defined work as applying a force to make something move through some sort of distance. So we could also say energy is the ability to apply a force over a distance, right? Just putting in the definition for work into that definition for energy. If I didn't have energy stored up in my body, I couldn't pick up the pen. And depending on how much energy I have stored in my body, I might be able to pick up the pen, but maybe I can't pick up something heavier. It depends on how much energy we have stored. So energy is the ability to apply a force over a distance. Another way to define energy is it's the ability to cause a change in the structure of an object or the motion of an object.
When you say over a distance,
Mm-hmm.
what does that mean?
Just means that it has to move from point A to point B.
Okay.
Yeah, it doesn't have to go in a straight line necessarily, it just has to change its position.
Okay.
So causing a change in structure. Maybe I take a piece of paper and I tear it. It's still paper, but I've changed its structure. Maybe I find a piece of soft metal and I use a hammer and I pound it to change its shape. Okay, it's still that metal, but I've changed its shape. So we can change the structure of things, but it takes energy to do that. We can also change the motion of things. What does a force cause? Based on what you learned last semester, what does a force cause in objects?
Energy?
Well, we need energy to be able to apply a force, but what would the force cause an object to do?
Motion.
What about its motion?
Accelerate.
Yeah, it's going to accelerate. F equals ma,
Oh.
right? So if I apply a force, that object will accelerate. That object will change its motion. So what we're saying here is energy is the ability to accelerate an object, which means we have the ability to apply a force, because forces cause objects to accelerate. So hopefully you're seeing how we're really thinking through forces and work and distance, all these terms we used first semester. Now we're integrating them in a new way to define these new concepts. We had to learn what force was and what we mean by distance to understand what work is. And we have to understand what work is to be able to fully understand energy. And we had to know what acceleration meant, because that's what the change in motion would be caused by a force, which requires us to have energy to apply. Like I can't push on something without energy. I can't pull on something without energy. All right, now power is slightly different. It's related, but it's a slightly different concept. Power is the rate at which you do the work. How fast or how slow you do the work. Made me think of a lab I was kind of wanting to do, but Mr. was missing a class. All right, so if we do that lab, we'll have to maybe use the back stairway. There's a lab that I do some years so that you can get a power rating for your own body. But you have to run up and down stairs, so I think it would be a little distracting out there for Mr. Gillespie's class, but maybe we can do it here. We might just not do that this year, we'll see. All right, the rate at which work is done, how fast you do the work or how slow you do the work. In other words, it's the work done per time. The work done per time. So the work done per hour, or the work done per minute, or the work done per second, some unit of time. All right. Oh, I meant to mention this earlier and almost forgot. Tomorrow is just the second day of the week for us this week, but it's the Thursday schedule. So you guys will come in, it's right after first period, yeah. So we'll be second period tomorrow at 10 o'clock. So just making sure, because we're different on Tuesdays and Thursdays, and tomorrow's the Thursday schedule, just like the day. It is Thursday, so we're using the Thursday schedule. All right. All right, so now we've defined it. Those top 2 bullet points are just the definitions we gave before. Applying a force to make something move through a distance, or transferring the energy from potential to kinetic, or to a spring, or a gravitational, some form of changing how that energy is stored. But here are the 2 equations, and really the first equation is the one that I want you to focus on. The second one is going to be more consistent with when we talk about conservation of energy next week. We might actually start talking about it tomorrow, but it'll be the focus of next week. And so the first equation there, W equals FD, that's the first one. Work equals force multiplied by the distance the object moved. Well, what is the unit of force?
Newtons.
Newtons. How do we measure distance?
Meters.
Meters. So if we're taking newtons times meters, the units for work must be Newton meters, or newtons times meters. But do you guys remember how a Newton is really a kilogram times meters per second squared, because it's mass times acceleration? So it has that kind of funky unit, but we just abbreviate it, we shorten it. We can shorten this down as well, because technically a Newton meter would be a kilogram times meters squared over second squared. That's really what the overall units of work are, but we shorten all that down to just be a J, which stands for joule. So just like we abbreviated all this down to make it a Newton, we're going to abbreviate all this down to make it a joule. So work has its own abbreviated unit, special unit, which we call a joule, and we just use capital J. So it's not pronounced, or it's not spelled like a jewel on your diamond ring or something like that. It's not that kind of a joule. It's actually named after James Joule, a scientist. So that's why it's spelled this way. Now the second equation, W equals triangle KE. What's a triangle mean again when we see it in an equation?
A change of.
Change of. And any guess as to what KE is an abbreviation for?
Kinetic energy.
Kinetic energy, yeah. So we're going to focus on that later, that work can also be the change in kinetic energy, because we see up here the transfer of energy from one storage mode to another. So did we make it move more? Did we make it move less, faster, slower? How did we change its motion? And how we changed its motion is another way we can find out work, but it's an indirect method. So we're going to save that till we talk about conservation. So the first one is the one I want you to focus on, applying a force to an object to make that object move a distance. All right. Questions about that equation or the units? All right. So a couple of things we might say would be work in real life are also work in physics. So this guy is getting a workout. Well, maybe he's not really doing a workout, he's doing a competition, but he's worked out in order to build up the strength to compete. And he's applying a force to push that barbell through a distance, right? There's a force, there's a displacement. So is he doing work?
Yeah.
Yes. He's got an upward force and the object's moving upward. He has done work on that barbell. He's applied a force that caused it to move a distance. All right. Is the gentleman here, he may say, hey, wife, I'm going to go out and do some work in the yard. Is he really doing work here? Is he applying a force to make something move a distance? Yeah, he's applying a force to the lawnmower, and the lawnmower moves through some distance. So he said work to his wife, whether he meant the physics aspect of it or not, he really is doing work out in the yard, pushing on the mower and causing it to go a distance. So both of those examples would be cases where we'd say, yeah, this dude is definitely working, and this guy also is working in two different ways. But in those cases, it actually does mean physics work, because in both cases, they're moving an object, it's covering a distance because of the force that they're applying. Okay? Now, is all of the force this person's applying to the lawnmower making the mower go forward? Or is only part of the force he's pushing with making it go forward? What do you think? Is all of it making it go forward, or is only part of it making it go forward? Part of it. This force, that he's actually pushing on the handle this way, right? Whenever we have a force or any kind of vector that's at an angle, remember how in first semester we could break it into x and y components? Which component is the only part making it go along the ground? The x. But he's pushing down a little bit too, right? How could he be more efficient at using more of his force to displace the mower?
By the it might go parallel.
Yeah, if he got down lower and lower and lower, but then that wouldn't be very comfortable, right? So sometimes we sacrifice efficiency for comfort or ease. Pushing a mower like this all day wouldn't be very comfortable. It would be more efficient in terms of the amount of force we'd have to apply, but not that comfortable. Whereas now I can just comfortably push it this way. Okay, so sometimes we don't use all the force we're applying to accomplish work, only some of the force we're applying accomplishes the work. It has to be parallel to the object's motion. So in this case, it's only the X amount of his force that's making the mower move sideways. The Y is technically pushing the mower down into the ground, which isn't very helpful, but that's really all it's doing. All right, so we're gonna break this down, kind of wrap this up here in the next couple minutes. Work is force time distance, but like we talked about there with a lawnmower, it's only the force component in the direction of the motion that matters. So if the box is moving left to right, it's only the force component that's left to right. Now this guy looks like he's kind of kneeling down to push, so he's not pushing down as much. So he is pushing it more parallel, right? He's trying to become more efficient with how much of his force is actually doing work on the box. But if he was standing straight up and down, part of his push would be into the ground, and that's not really doing work because the box isn't moving down, right? The box is only moving sideways. If I wanted to push this table, pushing it at a really steep angle, I'm mainly pushing down, right? So it doesn't really make it move sideways. But if I push it this way, now I can actually make it slide, right? So changing the angle of the push would make more of the force be parallel to the motion. And it's only the force component that's parallel to the motion that matters. It has to be in the exact same direction. So if he bends down and tries to get his force directly in line with the displacement, he's efficient. He's using all of his force to do work. All right, so let's talk through a few examples and try to decide by the physics definition and what we've learned so far, would these be examples of physics work or not? So a man holds out a heavy concrete block at arm's length for 10 minutes. Is he doing work according to physics? No, why not?
So it isn't going anywhere, you're just holding it.
Yeah, it's not going anywhere, right? There's no distance. There's force, he's applying force, but the block isn't moving, and the block has to be moving through some distance for it to be work, right? A student pushes the car down the street. Does that work according to physics?
No. Or yes,
Yeah.
yes,
Is the student applying a force?
yes.
Does the object move?
We don't.
Does the object move in the direction of the push?
Yes.
Yeah, we assume that he's pushing it in the direction that it goes, otherwise it wouldn't go down the street, right? So that seems like work. How about a woman holds a large box over her head while she's walking down the street?
No,
Why not?
because it's not parallel. to the
Yeah.
force.
Her force is what direction?
Up.
Up. But is the box covering a distance upward?
No.
No. So now you could argue this a little bit. If she's standing still and she just started moving, she would have to push forward to get it moving, right? So like right at the beginning when she started moving, she'd have to, but if she's already moving, Newton's first law, an object in motion stays in motion. So once she's got it moving, it's gonna keep moving forward, right? And so her force is upward, but the box is moving sideways. They're perpendicular to each other, not parallel. So according to physics, that's not work. Will her arms get tired? Eventually. She is doing a workout, but it's not physics work. A child pushes a cart along the sidewalk.
Works.
Yeah, there's a force, the object's moving. The force would have to be somewhat, at least, in the direction of the moving. Maybe not purely, it might only be part of it, but there's going to be some work being done there. Okay, so there has to be movement, and the force has to be applied, at least in part, in the direction that the object moves. Okay? All right, so I've got a worksheet here to help you practice that equation. We just have a little bit of time, so see if we can get started on this one. So this is the work equals F times D equation that we put on the board over there. And I didn't notice a typo until I printed it, so I didn't want to reprint them, so I scratched it out with red pen, but if you look at the last question on the worksheet, and Lauren, is it easier for me to email this to you? Would that be the best way to get it to you? Just email you a copy of it? All right, I'll do that. So on the last question, number 5, Lauren, for yours, it's already corrected, so you'll get the right version of it, so you won't have to do anything. But for those of you in class, you might notice on the very last number in question number 5, it says 1,800 seconds. It should just be 18 seconds. Because it talks about a boy pushing a sled and it slides for a while. I don't think it would slide for 1,800 seconds. It would only be 18 seconds. So I tried to cross out those 2 zeros. All right, so use these next few minutes to try to solve as many of those 5 questions as you can, and I'll go ahead and email it to you, Lauren.
What is KN?
Kilonewtons. So 65,000 newtons. Lauren, is it better for me to send it as the Word form or PDF?
Either is fine.
Okay. Do you have a preference? Because I have both.
Maybe
No preference?
PDF, I guess.
PDF, okay. Sometimes if students are using a Macintosh computer or Apple-based computer, the Word document gets messed up, so. Sorry, my computer's going really slow.